Welcome, cosmic explorers, to Tachyon Signals. We often picture black holes as the ultimate cosmic prisons, points of no return where gravity reigns supreme and nothing, not even light, can escape. They seem like eternal monuments to destruction, swallowing everything that ventures too close. But what if that picture isn't entirely complete? Prepare yourself, because the mind-bending reality involves quantum physics, legendary scientists, and the astonishing idea that black holes might actually fade away. Let's start with the classical picture, the one painted by Einstein's theory of general relativity. When a truly massive star exhausts its nuclear fuel, it can no longer support itself against its own immense gravity. It collapses catastrophically, crushing down into an infinitesimally small point of infinite density, a singularity. Surrounding this singularity is a boundary known as the event horizon. Think of it as the cosmic point of no return. Cross that threshold, and the gravitational pull becomes so overwhelming that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon can ever get back out. From this perspective, black holes are cosmic vacuum cleaners, relentlessly growing as they consume matter and energy from their surroundings. They seem indestructible, permanent fixtures in a universe. Once formed, they appear destined to exist forever, or at least until the universe itself ends. This view dominated astrophysics for decades. It's intuitive, based on our understanding of gravity as an attractive force. If gravity is strong enough to trap light, how could anything possibly leak out? This picture seemed simple, elegant, and terrifyingly final. But the universe, as we've learned time and again, loves throwing curveballs, especially when quantum mechanics enters the fray. In the early 1970s, the brilliant physicist Stephen Hawking was pondering the bizarre intersection of general relativity, which governs gravity, and the large-scale structure of the universe, and quantum mechanics, the physics of the very small. These two pillars of modern physics work incredibly well in their own domains, but trying to combine them often leads to contradictions and paradoxes, especially in extreme environments like the edge of a black hole. Hawking was particularly troubled by what happens to information that falls into a black hole. In quantum mechanics, information is fundamental. It can be transformed or rearranged, but it can never be truly destroyed. Think of it like scrambling the letters of a word. The letters are still there, just in a different order. However, general relativity seemed to imply that once something crosses the event horizon, all the detailed information about its quantum state is lost forever, hidden behind that impenetrable veil. This conflict became known as the black hole information paradox. If a black hole swallows a particle, what happens to the quantum information describing that particle? Does it vanish, violating a core principle of quantum mechanics? Or does it somehow persist? Hawking's attempt to reconcile these theories led him to a truly revolutionary discovery. To understand Hawking's breakthrough, we need to dive into one of the strangest concepts in quantum mechanics: the quantum foam. Contrary to our classical intuition, empty space isn't truly empty. On incredibly small scales and for fleeting moments, the vacuum of space is a bubbling cauldron of activity. Pairs of virtual particles, a particle and its corresponding antiparticle, spontaneously pop into existence, borrowing energy from the vacuum itself, as allowed by Heisenberg's uncertainty principle. Normally, these virtual particle pairs exist for only an infinitesimal fraction of a second before they annihilate each other, repaying their energy debt to the vacuum. It's like a constant subatomic fizzing happening everywhere, all the time. You have an electron and a positron appearing, existing for a blink, and then vanishing back into nothingness. This happens constantly throughout the universe. But what happens if one of these virtual particle pairs appears right at the edge of a black hole's event horizon? This is where things get incredibly interesting, and lead directly to Hawking's startling conclusion. The intense gravitational environment near the event horizon can dramatically alter the fate of these fleeting particles. Imagine a virtual particle pair, say an electron and a positron, popping into existence right at the event horizon. Several things could happen, but the crucial scenario Hawking identified is this. One particle falls into the black hole, crossing the event horizon, while its partner manages to escape out into space. Because its partner has fallen into the black hole, and can never come back out to annihilate it, the escaping particle can no longer be considered virtual. It becomes a real particle, carrying real energy away from the black hole. But where does this energy come from? It can't just appear from nothing. That would violate the conservation of energy. The energy required to promote the escaping virtual particle into a real particle is effectively stolen from the black hole itself. Think of it like this. The particle falling in can be thought of as having negative energy relative to an observer far away. Because gravity is so strong, it pulls energy down. When this negative energy particle falls into the black hole, it reduces the black hole's total mass energy. To balance the books, the escaping particle carries away positive energy. According to Einstein's famous equation, E equals mc squared, energy and mass are equivalent. So by radiating away particles with positive energy, the black hole is actually losing mass. This steady trickle of particles escaping from the vicinity of the event horizon is what we now call Hawking radiation. It's an incredibly subtle quantum effect, born from the interplay between gravity and quantum field theory right at the edge of oblivion. The consequence of this constant emission of Hawking radiation is profound. Black holes are not eternal. They are slowly, incredibly slowly, evaporating. By radiating particles, they lose mass and energy over time. As they lose mass, their gravitational pull weakens slightly, and their event horizon shrinks. Now, for the types of black holes we typically observe, those formed from collapsed stars, stellar mass black holes, or the supermassive giants lurking at the centers of galaxies, this evaporation process is unbelievably slow. The rate of Hawking radiation emission is inversely proportional to the black hole's mass. This means larger black holes radiate much less intensely, and evaporate much more slowly than smaller ones. A black hole with the mass of our Sun would take around 10 to the power of 67 years to evaporate completely via Hawking radiation. That's a 1 followed by 67 zeros. To put that in perspective, the current age of the universe is only about 13.8 billion years, or roughly 1.4 times 10 to the 10 years. So stellar mass black holes will far outlast the current era of stars and galaxies. Supermassive black holes, millions or billions of times heavier, will take vastly longer still, timescales that dwarf even 10 to the power of 67 years. However, the theory also predicts that if much smaller black holes were formed in the very early universe, so-called primordial black holes, those with sufficiently low mass might have already evaporated completely by now. And as any black hole evaporates, it shrinks, and the rate of radiation increases. In its final moments, a tiny black hole would radiate away its remaining mass in a final, intense burst of energy and particles. The existence of Hawking radiation fundamentally changes our view of the ultimate fate of the cosmos. In the unimaginably distant future, long after the last stars have burned out and galaxies have dispersed, the universe might enter a black hole era. During this epoch, black holes could be the dominant large-scale structures remaining. But even they are not permanent. Over truly astronomical timescales, Hawking radiation will ensure that even the most massive black holes eventually evaporate. What happens then? The universe could eventually become a cold, dark, and incredibly dilute soup of photons, neutrinos, electrons and positrons, the remnants of evaporated black holes and decayed matter. This scenario is sometimes referred to as the heat death of the universe, a state of maximum entropy, where no further work can be done. The final moments of black hole evaporation are particularly intriguing. As a black hole shrinks, its temperature increases, and the Hawking radiation becomes more energetic. The very last second of a black hole's life could involve a powerful burst of gamma rays and other high-energy particles. Searching for such bursts could potentially be a way to detect the evaporation of hypothetical primordial black holes, if they exist. Hawking radiation suggests that even the ultimate gravitational prisons are temporary, destined to dissolve back into the fundamental fabric of spacetime, contributing a final, faint glow to the twilight of the universe. While the theory of Hawking radiation is widely accepted within theoretical physics as a necessary consequence of combining quantum mechanics and general relativity near an event horizon, directly observing it is an entirely different challenge. The problem lies in the incredibly low temperature associated with the radiation from astrophysical black holes. The temperature of a black hole due to Hawking radiation is inversely proportional to its mass. For a solar mass black hole, this temperature is only about 60 nanokelvin, 60 billionths of a degree above absolute zero. This is far, far colder than the cosmic microwave background radiation, CMB, the leftover heat from the Big Bang, which permeates the universe at about 2.7 Kelvin. Any Hawking radiation emitted by such a black hole would be completely swamped by the CMB and other background noise, making it effectively impossible to detect with current technology. Supermassive black holes are even colder, making their radiation even fainter. Scientists are exploring alternative avenues. One possibility is searching for the final bursts of radiation from evaporating primordial black holes, though none have been definitively detected so far. Another approach involves creating analog black holes in laboratory settings. These are systems, perhaps using fluids, Bose-Einstein condensates, or even light pulses in optical fibers, that mimic the properties of an event horizon. Researchers have claimed tentative detections of stimulated Hawking radiation analogs in these systems, which provides some experimental support for the underlying physics, although it's not quite the same as observing radiation from an actual astrophysical black hole. Detecting genuine Hawking radiation remains one of the major observational goals in fundamental physics, as it would provide crucial evidence for the interplay between gravity and quantum theory. So, are black holes fading away? The groundbreaking work of Stephen Hawking, born from the clash between general relativity and quantum mechanics, strongly suggests they are. Through the bizarre quantum process of virtual particle pairs interacting with the event horizon, black holes emit a faint thermal glow, Hawking radiation. This radiation carries away energy and mass, meaning that over incomprehensible timescales, even the most massive black holes will eventually evaporate, leaving behind only a faint whisper of radiation. While detecting this radiation directly remains beyond our current capabilities for astronomical black holes, the theory stands as a testament to the power of physics to reveal the deepest, most counterintuitive secrets of the cosmos. Black holes aren't forever. They are just incredibly patient participants in the universe's long, slow dance towards entropy. Thank you for joining us on Tachyon Signals as we explored the mind-blowing truth of Hawking radiation. Keep looking up, and keep questioning.